I was in the middle of one NSF-funded research project on augmented reality visualization for civil infrastructure and construction applications. And in 2008, coincidentally, we had just gotten another grant from NSF to continue working in that area. And while interacting with Suyang, even at that time, it was kind of clear that somehow he had made augmented reality kind of a mission of his life, at least for the near term of his graduate studies. And I was luckily sharp enough to recognize that and recruited him to come work in our research group while he pursues his Ph.D. So to make a long story short, that decision has paid a lot of good dividends for our research group, and I believe Suyang has made some then everybody will be requested to excuse us. Then the candidate himself will be requested to excuse us, and after which everybody can come back together again potentially. Right? So thanks once again, and Suyang, floor all yours.
Thank you very much, Professor. And for those who just came in, there's some homemade cake over there, which is very delicious. Don't miss it. Okay. Good afternoon, everyone. Most honored committee members, my dear friends, and most welcome guests. Today I want to defend my PhD thesis with the title as Scalable and Extensible Augmented Reality with Applications in Civil Infrastructure Systems. Well, I don't want to be that serious. Actually, I just want to address two questions. The first one is, what can augmented reality do for civil infrastructure systems? And John Kennedy says, ask not what the augmented reality can do for you, but ask what you can do for augmented reality. So that's the second question I want to address. What can we do to explore the potential of augmented reality? Since we have a lot of guests who might not be very familiar with augmented reality, so let's start with what is augmented reality. If you search online, there are classic definition about augmented reality with 3 items. First, the alignment of virtual and real objects. Secondly, the coexistence of virtual and real objects. And thirdly, virtual and real interact in real-time frame rates. Well, that's very abstract. That said, a picture worth 1,000 words. And more importantly, we have 4 pictures here. Let's try to figure out what's the definition of augmented reality in a PC era. In manufacture, the engineer can make up a digital mock-up of the design car and superimpose that on the existing assembly line to see whether that model fits. Or for a doctor, he can superimpose the X-ray image on the face of the patient so that for a better diagnosis. And for students, when they open the static book, they might expect some dynamic models of the images popped up right in front of them. And for gamers, if you get tired of always playing games, shooting games in front of the PC, you can play some video games in real life. And now, we're not in the PC era. We are in a post-PC era defined by Steve Jobs, where most people own mobile devices. And we begin to add the 3rd or the 4th dimensions called location and orientation to our knowledge base. So that's why augmented reality began to thrive on these devices, like location-based service. You can search for the nearby restaurant. Or if you, like me, who get very poor memory to memorize people's name, and then you can point your device at people's face, and it can superimpose a Facebook tag and a Twitter tag for you, and right for you to click. Or more recently, it's getting very popular and heated up, which is called Google Glass. It integrates a lot of sensors into this extremely lightweight glass. And we have seen a lot of celebrities being advocate of this. That's about augmented reality. But we still need to come to the ground about what can augmented reality do in civil infrastructure systems. So we want to figure out what's the advantage of AR in civil. When we talk about civil, we think about building things. And we also think about modeling things. And sometimes the modeling can be very expensive and time-consuming. But with augmented reality, you can largely replace the modeling work of the existing environment. Or, because the coexistence of real and virtual, we can begin to conduct field tasks with augmented reality. And let's be more specific. Researchers have identified 8 specific areas where augmented reality could be useful, like excavation, coordination, inspection, etc., etc. And let's take a look at a few examples. First, excavation. It's about visualization of the underground pipelines so that operators can see it to avoid the collision. Inspections. You have some as design model and you have as build. You want to compare the discrepancy between the two to find out what you need to do about it. And supervision. Supervision is about superimpose the schedule on top of your job site so that you can find out whether you're lagging behind or you're on track. Strategizing. It's about a plan for the future. You want to do some simulation to see whether that works, to find out the economic and efficient way to that. And that's some examples about augmented reality in civil infrastructure systems. And it's a brief answer for the first question we just talked about. And now, let's get to the juicy part. What can we do to make those things happen? Well, before we get into these varieties of applications, there are always some technical issues that you have to confront. The first thing is called registration. As I mentioned before, it's about alignment of the virtual and the real objects. And occlusion, which means you have to create an illusion that the virtual and the real coexist together. And after we solve this problem, we can begin to get to a lot of varieties of applications. And because all these applications involve these technical challenges, that's why we come up with this idea of integrating these solutions into an open and scalable framework so that the third party can just focus on their domain-specific questions and don't worry too much about the underlying registration and occlusion problem. So, at this framework, we call it a nickname, a cute name called SMART, which is Scalable and Modularized Augmented Reality Toolkit. And there are 6 modules of that, which is exactly how I code them on my PC. And I have 120 pages documentation about this code on my Ph.D. thesis. I think most my committee members have seen it, and Professor Yemi asked me, do you really want to print that 120 pages out? I said no, but I have the interest to have all the audience go through each line of my code through the presentation. Just kidding, I'm just kidding. What I'm going to do is to explain the underlying principle of each module and how I organize them in this framework. Let's start with the Smart Crew. Smart Crew is a module that organizes a collection of virtual elements. It has 2 employees, AR class and AR object. Class is something you build or you load from the disk. You can understand that as a person called Bob. And then but Bob received some training and become capable of doing the work of masonry, not masonry. Don't show ignorance of in a PhD thesis. And then maybe some other training, ironwork, in this section. So that's how we handle that class. We apply apply some transformation to the class so that the AR object becomes an instance of the class in the augmented space. Because you have crew, so you need to keep a roster of those crews. And those rosters are stored in something called smart site. And not only roster, you need to allocate them somewhere in the construction site, right? That's the job of AR graph. And also AR controller, which receives the user input, you can understand as a change order on the construction site. And here, we're more interested in the middle part, which is called AR graph. It's about how to allocate those crew correctly on the virtual side. This is what I talked about registration. Now we're going to get a little bit technical. The registration in augmented reality means align the virtual and the real objects together. And that's the job of smart motion. Smart motion takes the location and orientation of the real cameras and magically compute the registration results and deposit that in the AR graph so that AR graph knows how to allocate those crews. Well, when I say magically, it's not really a magic. It's actually pretty simple. Think about how you take pictures in a real life. Okay? So, when you begin to take pictures, you ask someone to be somewhere and make a pose. And then you position your camera and you rotate it or whatever. And then you adjust the lens of your camera and then boom, you take the pictures. That's exactly the 4 steps over here. You position your camera, you ask the virtual or the real objects standing in a certain location, you adjust your lens, and you take the pictures. But it's not that simple in the augmented reality because there is virtual and real. For the real part, we have for example, the RGB camera. But for the virtual part, we need the virtual camera be aligned with the real camera so that the virtual objects can be aligned with the real objects. That's why you need to track, you need to track the location and orientation of the real camera and adjust the parameters of virtual camera according to this. And the same thing, the real camera has its own field of view and its own principal point. So you want to make sure you calibrate your real camera and put that parameters into your real camera. Your virtual camera. I just said that I need to track the location of the real camera. And here we use a GPS to track the location. But you can see that the GPS is actually placed on top of the helmet while the camera is in front. So to make sure you track the correct location of the camera, you need to do some mechanical calibration of this. And I believe that calibration is actually a little bit beyond the scope of the defense. But if you're interested, we can definitely talk about it in the prep section. And here it highlights that. Here's just an example about how I align the virtual objects to the real one. The white box is a 2x4 box, and I create a digital mock-up of that with the same size but in the virtual world and align them with a different pose. So that's the job about smart motion. It's about align virtual with the real objects. And it is information of location and orientation of the real camera. I just said I can get the location information from the GPS. So that's actually the job of something called smart sensor. And smart sensor use AR location and AR orientation as a common interface to smart motion. But since I said I get that from GPS, why don't I just call it AR GPS? Because you can not only get your location from a GPS, but you can also get that, for example, an IMU, an inertial measurement unit. Or you can just simulate that, give them an arbitrary number. And that's the same thing for an orientation. You can measure that by the compass, or you can do that with a total station, or just simulate that. That's how smart sensor in the abstract layer between the smart motion and the physical device online. Well, that's the device we use, GPS an electronic compass. And we have to place it rigidly and economically on the holding devices. I call this augmented reality mobile operating rover with the nickname of Armor. Here is a front view. I think this person is not here, but you all know who he is. Here the GPS is anchored on top with the compass in front, camera. This head-mounted display is occlude your normal vision to superimpose the augmented image in front of you. And this is a back view of that. Because you are using a GPS, you need a receiver, and also you need something to compute the augmented algorithm. So you need a camera, you need a laptop. And here I want to mention that it's about the accuracy of the GPS. Because the accuracy of the GPS and the compass is very essential for you to align the virtual and real objects. That's why we adopt some GPS called real-time kinematics with the accuracy of 2 centimeters on the horizontal ground. And to do that, you need a radio to receive the correction from a base station setting somewhere. And that concludes the smart sensor. But we're still missing something. First, we need to organize the whole thing together. That's why you always need a foreman. You have a side foreman in charge of smart side. You have sensor foreman in charge of smart motion and smart sensor. And don't forget, there's one more important piece. Video. We are dealing with augmented reality. We want to show the real background, so we need a video here. But you may think, why don't we just call it like an RGB reader so that we read the images and put that onto as a backdrop of the augmented space? Because the problem is, you can not only get your real background from a web camera, you can also get that from engineering camera, or even something called time-of-flight camera. This camera, it doesn't give you an RGB value. It actually gives you depth map of the whole environment. Or even more, you can get a hybrid camera with RGB camera on top and depth camera on the bottom. So, the same principle here. Smart video provides a common interface to these different kinds of camera so that it looks transparent to whatever sits on top of that, just like what we talked about with smart sensor. But if it just provides a common interface, then I can simply integrate that to the smart sensor. The reason that I separate that is that smart video is going to handle some other important work called occlusion. We have been keeping talking about the alignment between the virtual and the real objects. But don't forget, there's a second definition called the illusion that real and virtual objects coexist. And one of the illusions is that you need to correctly solve the spatial cue between the virtual and real. For example, traditionally, if I'm using an RGB camera, when you project the real thing onto that camera, the distance information is lost. So there's no way but to put the real images as a background and always superimpose the virtual objects on top. But it's not always this case because, for example, this balloon can be behind the tree instead of in front. This shows a correct occlusion effect, while this is not. So that's why we need to solve this occlusion issue. How? Well, there's an old saying in China that says, if you don't know how to live your life, then simply look at your neighbors. Here, we are looking at OpenGL. OpenGL is a graphics library where it helps you to create 2D or 3D images, geometries, and etc. And for OpenGL to solve the occlusion issue, it maintains two buffers, a color buffer and a depth buffer. A color buffer is what you see on your screen, right? With RGB values. So you know the shape, the attribute of the geometry. Depth buffer is not something you can see, but it's very important. It helps you to make depth comparison and decides which part you can see, which part you cannot. Let's make a comparison. For example, I want to render a picture frame on the back of the conference room in the OpenGL, which means it's suppose it's virtual. And its color, say, is blue. And it's like 7 meters away from me. So when I render that frame, I put the blue pixel into the color buffer and put a 7 meters distance in the depth buffer. And then, suppose I have a camera right in front of me and occlude that blue frame. Then in this case, when I render that, I'm going to put, first, suppose this is 1 meter away from me, I'm going to put a black, this is black, put the 1 meter in the depth buffer, compare that with the 5 meters. And since 1 meter is smaller than 5 meters, it's going to replace the 5 meters in the pixel in the depth buffer. And then it put a black pixel in the color buffer. And that's the way you solve an occlusion issue in the OpenGL environment. So, from the experience from OpenGL, if we have the same information about the real background, like a depth image, and then we can simply write that into the depth buffer. And later on, when we begin to render the virtual objects, we can make a comparison between the depth information and decide who gets occluded and who gets shown. And to get that information, we have a magic camera called time-of-flight camera, I just said. It sends out modularized infrared light. And depending on the speed of light and its reflection time, it can calculate how far away the real objects away from the viewer. And fortunately, it also can capture the intensity message at the same time, but it's black and white. So we can just upload this information into OpenGL and solve the occlusion issue. But before we do that, we don't have that for free, because the intensity image you get, its intensity is very biased. So you want to rescale it to make sure it looks a little bit better. And another thing is about the depth value. Because OpenGL does not accept any values beyond 1. Why? Because of the perspective division over here. Let's use some figures to illustrate that. Suppose this is Optimus Prime. It's, say, 7 meters away from you. That's the physical distance, 7 meters. And then in OpenGL, it doesn't render everything. It only renders something that's between the distance of near and far. It's near and far, you decide it, okay? Anything beyond that is get clipped. And then go to the left bottom corner. It tries to scale this frostum into a canonical view volume so that the depth value will become from the range from -1 to +1. And then eventually further scale it so that the depth value between 0 and +1. So when you are in OpenGL, do as OpenGL do. Make sure you transform the distance in the same way as OpenGL so that it can make correct comparison between the real objects and the virtual objects. Wake up, showtime. This guy's first time playing with it. Seemed that he had a lot of fun with that. Well, if we are in the 1950s, I would be very happy about the effect, black and white. But come on, we're in the 21st century. We're even beginning to enjoy 3D movie. I'm not that ambitious, but at least I want to show you the RGB value. So, if you still remember, I talked a lot about how to align the virtual camera with the real camera, right? To make sure the virtual and real objects be aligned. We have the same problem here with the RGB camera and TOF camera, but with more difficult questions. Why? With virtual and real, you can force the virtual camera to share the same projection parameters with the real camera. But here, you get two physical cameras. You cannot simply smash them together and you get a line of view. And usually, you get this kind of hybrid camera with a video camera, RGB camera sitting on top, and a depth camera, QF camera, sitting at the bottom. And then, the problem comes. It doesn't share the same location, same orientation, and even worse, it doesn't have the same field of view, principal points, and etc. So, this time, since we cannot smash them physically, we have to do some kind of image registration to make sure they are aligned in the image space. Well, the first method that comes into my mind is something called homography. What is homography? It's actually simple. You have two cameras, right? You take a picture from two perspectives, and probably on that two images, you find some similar point or correspondent point. And you believe that the transformation from one point to the other can be transformed by a quadratic transformation. And if you have enough points, enough correspondence, you can solve that quadratic information. And then when you have new points, you can simply plug in that into the quadratic transformation and get its location on the other image. But this homography has the premise that these two cameras has to share the same location. Or if they do not share the same location, then they need to look at something very, very far away from the camera. That's the premise. And here, because we think this RGB camera and the DJI camera, their principal points, or you can see location, are very close to each other, we begin to make approximation and use homography in this registration process. You can see there's RGB image, a QF image, and these markers, their features are very obvious, so that you can easily establish the correspondence between the 2 points and try to align them. And here is an effect with occlusion disabled. You can see that even though I'm standing in front of the mini excavator, but it looks like it's just floating on top of me. But here, with occlusion enabled, you get a strong spatial clue about where the excavator is. Can everyone sitting in the back see clearly the effect? No? Should I dim the light a little bit? Can someone sitting in the back try to
Actually, you can point to specific features of.
Let's take this one for example. Here, this is the correct occlusion. I'm standing in front of the mini excavator. I don't know why I always like to sit in that. But here, without occlusion, it just superimposed the mini excavator on top of me. It looks like it's floating. But here, it shows that it's behind me, and immediately get a sense where the excavator is. So this is one way of handling the RGB and QF camera alignment problem. But since it's approximation, sometimes it works, sometimes it don't. And we want to find something that always works. And here comes with another approach called stereo projection. Let's see, there's a point over here in the 3D space, in the real world. And it gets projected onto the QF image space, called T2. And then it also gets projected onto the RGB image of T1. If we can back project the T2 to the X in 3D space and reproject it to the RGB camera, we can build the correspondence. This is impossible with two normal cameras because, as I mentioned, when you use RGB camera to take pictures, that distance information is lost. So when you try to back project, even though you know this point should be somewhere on this line, but you don't know exactly where it is. But with the TOF camera, you know the distance, so you know where it is on this line. And then you have the intrinsic projection matrix of RGB camera so that you can reproject onto the RGB camera image plane. And boom, the correspondence being built. And here shows an effect. Here is a female worker. It's up to you to guess who she is. And here it shows there's a lip scissor over here. And even though she is standing in front of it, this is the correct occlusion effect, but without occlusion, it always shows on top of that. Here, you get a better sense about the spatial clue. Don't worry about that. We're going to have a better view about what's going on here. Of course, now we can build a correspondence, but it's not enough. There is a quite big difference between you build a correspondence quick and build a correspondence very slowly. And this is a very miserable case where you build it very slowly. One more, get outside. Thank you.
So what is the frame rate here? Like 3, 4?
1, 2, because that correspondence is all being computed on the CPU, so it's extremely slow. But if we have some other technique, should I try to?
Yeah, just escape the PowerPoint.
Excuse me, because there's another committee member who is on the remote. Hello, Professor? Hello?
I'm still here.
Okay, that's great.
Not me calling, but I lost video a long time ago.
Oh, but you have the slides, right?
Yeah, I have the slides.
Oh, thank you. Let's keep going. So, we want to do that parallelly on GPU. And for that, we use something called rendered texture. I don't want to go into the technical details. It's not that it's too much for the audience, it's just that I'm not smart enough to explain that in 5 minutes. So, if you're interested, we can definitely talk about that in a prep session. And I know that Professor Irving definitely has some questions about this, and I'm definitely going to address that in the prep session. So, that concludes the smart video, which handles the occlusion effect. And now, that's all the part that can earn you maybe a second degree in computer science. But now what we can talk about, the application built on top of that, is what I hope can get him a degree in civil engineering. We have spent a lot of time talking about the smart and its component over here and all the technical challenges. And now, we are beginning to changing gears to look at all the applications building on top of the smart. The first one is something called RV-Scope, which is the Ph.D. thesis title of a former Ph.D. student of Professor Kamal. And his Ph.D. work is about visualize the simulated construction activities in an outdoor AR environment. And for that, he has built an authoring language called RV-Scope, where that language describes the articulated information about its geometry so that you can manipulate them in the augmented space. For you to do that, you need a authoring language statement parser, and also you need how to process those statements. So if you simply plug in the RV-Scope engine into the smart, and boom, problem solved. Now let's take a look at some examples showing RV-Scope running on top of smart, and more importantly, with occlusion effect enabled. Here is occlusion disabled. can see the mini excavator get occluded by the chunk of box in front. That's mad.
That's not true.
Except the female worker, all the other workers are uninvited. And here's another example in the outdoor environment. It's actually very simple for you how to figure out that a person standing on a virtual lift seeker. If you can see the magic over there. You can see this is an incorrect occlusion, so the lift scissor is always on top, which is looks just like floating on top of the sink. She's sitting there for a purpose. Let's see. I wish you are happy about the occlusion fact. And now we're changing gear to something else. It's about excavation. Visualize the underground utilities. And here we replace the Obisco API engine with something called Utility Factory. Why do we need augmented reality in excavation? Well, there's two reasons. First of all, if you are a little bit familiar with the life cycle of MISDIG, which is the one call center in Michigan. For example, if you are a contractor called Bob, want to get some water supply from the Hayward Street to the construction site on the G.G. Brown parking lot. There is existing pipelines running along the Hayward Street. But for you to get a water supply, you need to dig out the ground to get some pipeline connecting to the existing utility to redirect the water into your site. So the first thing Bob is going to do is to call the one call center, or MISDIG. And MISDIG sends out utility companies the wires to mark the ground to show where there's some utilities lies on the ground. But usually, Bob would describe in this way. I want dig on the Hayward Street. So utility surveyor will come and mark the whole street. But sometimes Bob is kind and says, I want excavate in front of the G.G. Brown. And then it makes their utility surveyor's life easier. Or it can be very precise, saying, I want dig right in front of G.G. Brown, in front of construction's front door, and on the grass. But usually, that's not the case. So, the utility surveyors usually mark double, triple, multiple of the real excavation zone, that extra workload. So, another problem is, after they mark on the ground, these markings can be very quickly washed off, destroyed by the traffic or the weather. This is right outside Gigi Brown, for the excavation activity happening outside. And I'm taking these pictures while those excavation activity going on. This is by the sidewalk. You can see the markings are still okay, but those, it's probably marked at the same time in the middle of the road. It's very difficult to interpret what it is. And even worse, when you begin to dig, after you dig out the layer of the soil or the cement, whatever, you destroy those markings. So it's totally up to the operator to interpret where the utility line is. And if they just come back from lunch, which is a typical case, they probably just forget where the marking is, and you can see how close the excavator teeth to the electricity power line. You can get a better idea from here. This is the teeth of the bucket. See how close it is. So that's why we want to solve this problem. First of all, when Bob sent a request ticket to Miss Dick, he just simply walked around the planned excavation zone, and then when the surveyor comes, you can see where they need to work, and then they digitally mark on the ground. When the operator comes back from lunch, they can just see where the digital pipeline is, so they will never miss where it is. And here I want to show you a conceptual video of the life cycle I just talked about, but it's not in augmented reality, but it's concept video in a Google Earth environment. Say if the contractor wants to excavate around Gigi Brown, Bayou Avenue, and Hillwood Street, he would just simply walk around with the GPS mounted. And here it shows what he sees. Okay, that finishes. So when utility surveyors come, they see the requested area, so they know where they need to survey and mark. And of course, they can mark digitally on the ground. And then the operator can see through the ground to find where the utility line is. And here is my initial efforts to visualize some pipelines provided by DTE Energy. And I superimpose on top of the ground. I won't go into the technical detail here, it's too much. And here is my latest efforts to overlay the digital layer on top of the ground so that utility surveyors can see where they need to mark. And then they just walk along the lines, they have to tap it and mark the on-the-ground utilities digitally on the ground. Here is, I guess you cannot see the color. Here is the electricity line with some attribute information shows its radius and depth. This is a cable. Blue stands for water, and this cyan stands for, I think, strength. And here, if you're familiar with the mistake, when it marks something on the ground, it doesn't mean that the pipeline is located exactly on the ground on the same location. You always have some buffer zone. So you want to make sure you have a buffer zone there, and when you're getting too close, instead of using an excavator mechanics, you have to use a shovel or your hand. And here, when the operator comes, it can see through the ground and have a better idea about not only where the utility is, but how deep it is. And here's some other views. Okay, that concludes the application about utility visualization. And next, we're going to go from outdoor to indoor. We're going to try to visualize the simulated process on a tabletop environment. And we call it Vidascope. I think half of you knows what Vidascope is. I don't expect so many welcome guests today, so I have to spend 1 minute talking about what is Vidascope. Vidascope is the Ph.D. work of Professor Kamat, and it tries to visualize the simulated construction process so as to validate and give the owner a better sense about what's going on in the simulation. And more importantly, it's very loosely coupled. It provides an open API so you can build your application on top of Vidascope. And because we're going indoor on the tabletop, the GPS no longer work in the indoor environment where it's invisible to the GPS signal. So instead, we have to use some vision tracking. And so Smart Motion, instead of using location and orientation, it began to use some vision tracking technique. And why we want to build a tabletop augmented reality? The basic idea is that for contractors, it has stacks of plans and drawings to discuss about. But the good thing is, it's very easy for them to collaborate on the paper drawings. And they can strategizing or planning, pointing to certain points on the paper base. But the downside is there's so many of them, it's very difficult to archive and maintain. But instead, on a computer, it's very easy to digitize and archive them. But you sort of lose the sense of collaboration on a computer screen. And that's why we want to use augmented reality to digitally archive those drawing plans or simulations, but still give the users the mobility to collaborate on the tabletop. And here just show some images showing, example showing laying a construction site on top of the ground. Here the Eagle window shows what has been observed by the RGB camera. And of course, because it's a collaboration, we want to show multiple videos. So we want to use multiple videos for the tracking. And here's the example. You can not only see the simulated construction site, but also your partner. And more importantly, when talking about vision tracking, there's a variety of ways of them. For example, what we have just seen here is something called fiducial marker tracking. And there's some other ways called natural marker tracking. I won't go into details, but basically for fiducial marker tracking, you need the camera to cover the whole marker. But with a natural marker, you can partially occlude them. For example, like in this case, even as my finger partially occlude that, it still shows the virtual content. And this is actually a natural marker developed by my colleagues. This natural marker is called KEG. So I'm not playing that word, but I want to say that this avatar is capable of adapting itself to multiple tracking methods. Again, I'm going to show the video quickly. This is a fiducial marker. You can see this is my desktop. You can rotate the marker to interact with the scene, or you can use just your mouse to drag the scene. Here to show some excavation activities with an excavator and a bunch of trucks. But you make sure you need to cover the whole marker of fiducial marker. But with a natural marker, which is KEG in this case, you can safely do part of the marker without lose the virtual scene. Of course, not too much. And this is model cameras. I'm not cheating. This is there's 2 cameras on that HMD, and there's another third cameras. It's very interesting. This is the same called the Reagan Airport, which there's an accident happened about like half a month ago, where 2 planes almost clashed each other. And these are the 2 users. This is the author of the KEG marker. All right. So we have to talk about both about outdoor application and indoor application. Now, this is the last applications. This is actually a little bit special because it's both outdoor and indoor. Why? Because we try to detect the damaged building. And it's actually an outdoor application, but because of the limited resources, we are forced to validate our algorithm in an indoor, or actually a virtual prototyping environment. Let's talk about why do we want to do that. I guess there's a lot of earthquake engineer over here, so please correct me if I'm wrong. After earthquake, some building collapsed, some building stands. So for those remain standing building, you want to access the soundness of the building before you reoccupy it. And one important index for you to estimate is something called in-the-story drifter ratio, which is the subtraction between the ceiling and the floor, divided by the height of the story. And then with that in-the-story drifter ratio, you can use that for building collapse simulation. I think a lot of people are nodding their heads. You seem very familiar. And simulation is not our job. Our job is to calculate the story drifter ratio. But we have a lot of challenges. For you to do the subtraction, you need to know where the corner is. For you to find the corner, you need to know where the edge is. So the first problem is, where is the edge of the building? Secondly, after you find the edge, you still need to find where is the corner. So there are 2 problems here. And this is our proposed solution in a virtual environment. You position a camera at a certain distance away from the building. You take pictures. You detect the edge of the building. And then you try to estimate the position of the corner. And here is a macro model. I think those structural engineers are very familiar. It's used for building collapse behavior simulation. And I create a counterpart. You probably cannot see clearly. I create a counterpart of that in a virtual environment, which is a wireframe model. And then I paste images right outside to make it look real. And the reason I want to do that is you have the wireframe model, you paste the texture, and then I begin to shift, because you want to create a damaged building, right? You begin to shift the vertex of the building. And when you shift it, the facade of the building is also going to drift accordingly, so that it can begin your edge detection of the damaged building. As I mentioned, there are 3 steps. First, position your camera. That's exactly the same principle I just mentioned in smart motion, where you want to align your virtual camera with a real camera. So the same principle applies here. Okay, now we want to detect the edge of the building. That's actually a good existing solution, something called line segment detector. It's very good and robust at detecting line segments. Don't be scared by all the redundant lines over here, because we know that approximately where the edges is. So we can easily filter out all this information, redundant lines, and get a clear edge of the building. Now, you get edge of the building. You want to estimate where the corner is. For you to get the 3D location of a corner, there is a very straightforward way, which you take a picture from one side, you find where it is on 2D image. And then you take pictures from another side, you find the same point on that image. And then you do the triangulation. That's how you calculate 3D points. So first, you need to find the 2D intersections on one image. And we have already detected the building vertical building edge, right? And the problem is, where is the horizontal building edge? Well, you can say with the line segment detector, if we can detect the vertical edge, we can probably detect the horizontal as well, like the outline of the windows, doors. I mean, sometimes it's true, sometimes not. You cannot always assume the outline of the window is the outline of the building edge. So we want to make it more comprehensive. So that's why we want to estimate that in an exhaustive way. Something we know is that where is the horizontal edge is before the damage, we call it horizontal baseline. And then we shift it. If you see the blue dashed line over here. For every distance it moves, we try to estimate, here is the distance it has moved, x, and for every distance it moves, we can calculate its radial location based on the triangulation I just taught. So ideally, if you make a good estimation, then what you have shifted x should match what you have calculated x prime. And if this getting very close to each other, then, then they will be a good candidate to my final solution. Once you get the 3D coordinates of the corner, and it's very straightforward to calculate the inter-story drifter ratio. You simply do the subtraction divided by the height of the building. And here, we first do that in a virtual prototyping environment. Virtual prototyping, the advantage of that is it allows you to test a lot of ambience parameters, like the distance between the camera and the building, image resolution.